Good evening, everyone. Warm welcome to all present in this meeting. On behalf of the Department of Mathematics at Wilson College, Mumbai, I heartily welcome Dr. Mahesh Naik, sir, for his second session in this IIT JAM Mathematics lecture series organized under the DBT Star Strengthening Scheme. As you all know, sir is an assistant professor in the Department of Basic Sciences and Humanities at SVKM's NMIMS Mukesh Patel School of Technology, Management and Engineering. And his areas of interest are in mathematical modeling and simulation, ML, optimization, and mathematics pedagogy. So thank you for taking out your valuable time. I now invite sir to start his session. Thank you.
Yes, thank you so much for the intro. Is my screen visible and am I audible clearly?
Yes, sir.
Yes, sir, it is visible.
Okay. Okay, so let's continue from where we left yesterday. We were talking about rank, and we have seen that rank is nothing but it's the number of linearly independent rows or columns in the matrix. Okay, and for a matrix A, we've used the notation row of A to denote the rank of the matrix. Moreover, we have seen that if m is the number of rows and n is the number of columns, the rank of A would be minimum of m comma n. Additionally, we saw some properties about the rank of A, B, and the relation with the product and so on. Okay, let's move forward and see the other way of calculating rank by using row echelon form. So what we saw yesterday was by using the submatrices, and if the largest submatrix has the determinant non-zero, then the order will be then the rank will be the order itself. But in case if it is zero, accordingly we can come down and we can keep on doing it till the time we get all submatrices non-zero of that particular order. Okay. Now when it comes to row echelon form, this is a form at which we can talk about the rank of the matrix. So before we proceed with getting the rank, a matrix is said to be in row echelon form if the following two conditions are met. So firstly, all zero rows of the matrix should be at the bottom. Okay. And the second and the most important thing is the leading coefficient with that I mean the first non-zero element in the row. The first non-zero element in the row, also known as pivot element, is always strictly to the right of leading coefficient of the previous row. Okay, so once the matrix has these two conditions met, it will be in row echelon form, and we will be able to talk about rank of the matrix. So the number of non-zero rows when the matrix is in row echelon form will be termed as the rank of the matrix. Okay, so in case if I have a matrix, maybe something like 1, 2, 3 in the first row, 2, 4, 6, and 0, 1, and 1. Okay, we can apply row transformations and bring it down to row echelon form. So in this case, we can go for R2 goes to R2 minus R1 to R1, which will give us 0. And doing an interchanging operation of R2 with R3, because as per the requirement, the 0 row should be at the bottom. And then we have 0, 1, 1, and 2, and 3. So is the matrix now in row echelon form?
Yes, sir.
Yes. So as per the requirement, the 0 row should be at the bottom. And when we look at the non-zero row, let us take this non-zero row. The pivot element is to the right of the pivot element in the previous row. Okay, so the conditions are met. Coincidentally, it happened that the pivot element is 1 in this case. Okay, but in row echelon form, this may or may not be 1. But then we have another form called as row reduced echelon form, where the pivot element should be equal to 1. Okay, so we can do an additional step of some row transformation to accordingly convert the same to 1. Okay, so row echelon form and row reduced echelon form. So both are same. In case of row echelon form, there is no compulsion of the number being 1. Whereas in case of row reduced echelon form, it should be equal to 1. Okay. Let's quickly look at some properties of rank in addition to what we saw yesterday. So we have seen that the rank of a null matrix is equal to 0. Rank of the product of the matrices is less than or equal to the minimum of rank of A and rank of B. Also, the rank of the sum of the matrices is less than or equal to the ranks of individual matrices. So rank of A and rank of B. Okay, same goes with subtraction. Okay. Also, if A and B are of order n cross n, then the rank of AB is greater than or equal to the rank of A plus rank of B minus n. If the matrix is a triangular matrix M cross n, in such case we also have this equality, rank of A transpose into A equals rank of A and also equals rank of A into A transpose. Okay, so this would be helpful when solving some of the problems which involve rank. Okay, let me just look at a problem that we can solve on the basis of this information. Let's look at this example. We have this matrix of order 5 cross 5, and we want to check the rank of the matrix. Okay, going with the technique of determinants will be lengthy in this case. So getting this matrix into row echelon form will be easier. So what operations can we do in this case?
I
It is equal to 5. Yes. So we can proceed with operations like R1 goes to R1 minus 1 by 2 R2, okay, which would make the later elements equal to 0. So, or otherwise we can have R2 minus 2 R1, which will make it all ones. And then the same operation can be followed very quickly. So let's say R2 goes to R2 minus R1, which will give us 0, 1, 1, 1 and 1 in the second row. The first row will be all ones. And then we can see the elements are almost similarly placed. Okay, then on the same lines, we can do operations like R3 goes to R3 minus R1, R4 minus R1, R5 minus R1, which will bring it to the row echelon form. Okay, and that will conclude that the rank of the matrix is 5 because there are 5 non-zero rows after this particular operation. Okay.
Yes.
Let's take one more example.
Sir, can we use column operation here?
We can use column. This is row echelon form, so it should be using row operations.
Sir, I mean to say that column form can be also be used by to calculate rank.
No. We cannot use column form to calculate the rank. It has to go. That's the reason the name of the technique is row echelon form. We cannot mix the two operations also. So if you're calculating the determinant or working with diagonalization and so on, then you can work with column form.
Okay, sir.
Is this question visible? It's a bit blurred.
Make it a little bit larger.
Large. So the question is, there is a set S of 3 cross 3 real matrices with A transpose into A equal to 1, 0, 0, and the remaining two rows are 0. And we are asked the set contains, whether the set contains an nilpotent matrix, a matrix of rank 1, a matrix of rank 2, a non-zero scale symmetric matrix. So we recently saw a property which said that the rank of A transpose into A equals rank of A. Okay. So based on that, we can confirm that the rank of A will be
Sir, 1.
1. So if the rank of A is equal to 1, we have option number 2, which is very clear about the same. Okay, so the property was rank of A transpose into A equals rank of A. And in this case, the rank of A transpose into A is 1. So rank of A is also equal to 1. And so a matrix of rank 1 will be the part of this particular set. Let's proceed towards the system of linear equations so that we can define some additional things like row space, column space, and eventually we can talk about the consistency. Okay. So system of linear equations. So a linear equation in variables, let's say x1, x2, up to xn, okay, can be written in the standard form. That is a1 x1 plus a2 x2 up to an xn equal to b. And if we have m such linear equations, the ideal representation would be a11 x1, a12 x2 up to amn xn equal to b1, a21 x1, a22 x2, a1 a2n xn equal to b2. Likewise, the mth equation am1 x1, am2 x2 up to amn xn is equal to bn. So that is a system of linear equations with m rows and n variables, and we can convert this into matrix form by extracting the coefficients a11, a12 up to a1n. Likewise, am1, am2 up to amn with the variables x1, x2 up to xn. And on the right hand side, we have b1, b2 up to bn. So we can denote this matrices with proper matrix notation. Let's say a x for this and equal to b. So that's my a, that's my x, and this is my b. So a is of order m cross n, x is of order n cross 1, and b is of order m cross 1. Okay. So we can have two types of systems of linear equations. So we can have homogeneous system where b will be equal to 0, and then non-homogeneous system where b is not equal to 0. Now, to talk about the solution of this particular system, whether homogeneous or non-homogeneous, we'll have to take help of rank. And before we proceed with rank, we'll define a matrix, that's augmented matrix, A augmented B, which is written by clubbing the values of matrix B into matrix A. So A11, A12 up to A1n. And then we have B1, B2 up to Bm. So it helps in observing the rank of A and A augmented B at the same time. Okay, so it is just the representation to separate all BIs from all AIs. Okay, otherwise we use the whole matrix for evaluation. So when it comes to the solution of the system, what we do is we look at the ranks and we talk about the consistency. So in case if I'm working with non-homogeneous system, so if I'm working with non-homogeneous system, which means B is not equal to 0. Okay, so in such case, what we do is we find the rank of the matrix A and we find the rank of the matrix A augmented B. Okay, and we look for the equality. So if the ranks are equal, accordingly the system is consistent, and if the ranks are not equal, the systems are not consistent. So if the systems are not consistent, by default there will be no solution. But if the system is consistent, there is a possibility where so consistency will guarantee the solution of the system, but there is again a possibility where the rank is equal to the number of variables, so equal to n, or there is a possibility where the rank of A can be less than n. So if it is equal to n, what we have is we'll get a unique solution to the system, and if it is less than n, then we'll have infinitely many solutions. So we'll have free variables, which will give us infinitely many solutions to the system. So any question till now?
No, sir.
Okay. Apart from this, if we are talking about homogeneous system, so we know that homogeneous system will be AX equal to 0. So is there a possibility that the system will be inconsistent?
No, sir.
No,
No. Why?
because
So because 0 is always the solution.
Yeah. So 0 is always a solution. The trivial solution will always be there. And so there is no possibility of inconsistency. So it is always consistent. But there is a possibility where we might have the rank of A lesser than the number of variables, okay, which will bring in infinitely many solutions. Okay. So looking at all of this, let's define some additional things with respect to the system. That is, let us talk about row space and the column space. Okay, so what will be the row space? So right now we saw the system of linear equations, and what we understand is we need a vector x, which is nothing but an n-dimensional vector belonging to Rn, which will satisfy the system. And there could be one or there could be many. So if there are many such vectors, accordingly they'll make up a set. Okay, and so we can talk about the spaces. So let's talk about the row space first. So row space of matrix A maybe. Okay, the matrix of coefficients. So in this case, if there are m rows, okay, R1, R2, likewise there are m rows. So the row space of A can be defined as the linear combination of all these rows. So that's K1, R1, K2, R2, up to K, M, R, M. Okay, where all these Ki's are scalars. So this particular space will be called as row space. Okay. Similarly, we can define column space, and the column space will be the linear combination of the columns. So row space will be a subspace of what? So if I assume A to be of order m cross n, my row space will be subspace of R
Rn,
m or R. So row space will
Rn,
be,
Rn.
yes. So each row is actually a vector of order n, and so this has to be subspace of Rn. Column space would be
Subspace of Rm.
Rm. The transpose of the column space will be subspace of Rm. On the same lines, we can also define the null space. So what is null space? So the space of all vectors which satisfy Ax equal to 0. So the space of all vectors x which satisfy this particular relationship Ax equal to 0 will be called as null space. It's non-empty because 0 will always belong to this particular set. And we can accordingly look at this in terms of the kernel of linear transformation. So now let us talk about the rank, the nullity, and the rank nullity theorem so that we can solve problems based on combination of all of this. Okay. So we have seen rank. Rank is the number of linearly independent rows when the matrix is in row echelon form or in general. Okay, nullity is also seen. All the vectors such that Ax is equal to 0. So now for a matrix A, for any matrix A, we can talk about the rank nullity theorem. So let's assume we have a matrix of order n cross n. Okay, then or let's say m cross n. Okay, then what will be the rank nullity theorem? So rank of A plus nullity of A will be equal to
Dimension of A.
So that will be equal to n in case this n in the case of this matrix. In case of linear transformation from V to V or V to W, we accordingly go for the dimension of the vector space. Okay, so this is how we can we'll be able to use this particular statement. So let's take some examples which will make us understand how to utilize once again. Let us get the example. let's begin with this. So we have Ax equal to B. Okay, and we are asked about the different possibilities of the solutions. So let's write down A augmented B, which would be 1 minus 1, 1, 1, 1, 1, 2, 3 alpha, and separated by 1, 3 beta. So to talk about the solution or consistency or anything, we'll have to get down to the row echelon form. And so let's go to the operation R2 goes to R2 minus R1, which would give us 0, 2, 0, 2, 3 alpha, 2 beta, and 1 minus 1, 1, and 1. Okay. We can also go for R3, going to R3 minus 2 times R1, which brings in 0, 5, and that's alpha minus 2. This will be beta minus 2 with 0, 2, 0, 2, and 1 minus 1. What next operation can we do? You can say R3 goes to R3 minus 5 by 2 R2, right? Which would give me 0, 0. R3 is alpha minus 2. And this would be beta minus 2 minus 5, and R2 is 2. So beta minus 7. Okay. Okay, so now the solution in this case. So if alpha is equal to 2, we are asked about the different possibilities. So if alpha is equal to 2, what will happen to the rank of A?
2.
Will be 2, because we'll have this entire row as 0. So 2. And let's not talk, so alpha equal to is the condition that we've considered. Let us also take the condition as beta equal to 7. So the rank of A augmented B will be equal to 2.
3.
Beta equal to 7. Alpha is equal to 2.
Yes,
So the
sir.
whole
It
row
is
becomes, it will be 2. And so this will be consistent and will have infinitely many solutions. Right?
Yes, sir.
Now let's go for other conditions where beta is not equal to 7, alpha is not equal to 2. Once alpha is not equal to 2, this condition is not required, because if alpha is not equal to 2, rank of A is going to be 3, and rank of A augmented B, irrespective of the value of beta, will be equal to 3. So this will be consistent and will have
Unique
unique
solution.
Yes. Okay, but if alpha is equal to 2 and if beta is not equal to 7, then rank of A would be
3.
3. Alpha is equal to 2, so rank of A will be 2, because this row will become 0 row. But
Sir,
rank of augmented matrix will be
3. I was talking about augmented matrix.
Okay.
3, sir.
So no solution. So when beta is equal to 7, beta is not equal to 7, and alpha is equal to 2, will have no solution. So which option out of this should we consider?
The fourth option.
Fourth option. Alpha not equal to 2. Let's solve one more. One. Take this one. We have this matrix A, and there is another matrix B. And these are the four options that we have in this case. So A and B are upper and lower triangular matrices, not completely dependent on rank, slightly towards determinants and inverse. So A is upper triangular matrix. Yes, so we
Option
can
A.
talk about option
A.
A, because in this case determinant of A will be non-zero because the diagonal entries are all non-zero. Determinant of B will be 0 because the diagonal entry is 0 and it's a lower triangular matrix. So not equal to 0 makes the inverse possible. Equal to 0 makes it singular. So this is the most better option.
So can
Let's
you
take-
show the previous slide?
Yes.
Okay, sir.
Let's take this question. So we have A, which is an encross in matrix, and Aij is equal to 3 for all ij. And then the nullity of A is asked. So the matrix is encross in matrix, and all the elements of this matrix are just 3. And we are asked nullity of A. So can we talk about rank of A first?
Sir, 1.
It will be 1 because there is only one linearly independent row. And so now we can talk about the nullity.
N minus 1.
N minus 1.
Be n minus 1. So we use
Rank nullity theorem.
here in this case. So a homogeneous system of 5 linear equations in 6 variables admits. So there are 6 variables. So we expect the solution in R6. There are 5 linear equations. So no solution in R6, a unique solution in R6, infinitely many
Infinitely many solutions.
infinitely.
Many solutions.
So there is a possibility where we can have the ranks equal to 5, which is lesser than the number of variables, which will give us infinitely many solutions. For unique solutions, we want the rank, which will be minimum 5 to be exactly equal to 5, which is not the case. No solution, it depends what is the rank. So the one of the possibilities will have infinitely many solutions. We might have no solution also depending on the rank. And the fourth one is talking about finite, but that is not possible because we have inequality in terms of number of equations and variables. Next,
So which one is most appropriate?
this one, infinite.
Okay, sir. Sir, for a MSQ, it will be another options also, like A and D also. No, sir.
Right.
I mean A and C also.
For some specific cases, we can have A and C also.
Okay.
So, but in homogeneous system, there is at least one solution. There is
Yes,
there is
yes.
no case for no solution.
Right.
Yes,
I
sir, it will
ignored that
have a
homogeneous
solution.
Right. I was just looking at the system. So it's homogeneous, so it has to have the solution, trivial solution. The only option suitable would be C. Next. Let's go to eigenvalues. Let's define eigenvalues and eigenvectors. I wanted to solve one example. One more. One second, if I can. Take this question. We have A as 205, 123, and minus 151. And the system of linear equations Ax equal to y has a solution only for y of the form x00, 0y0, or 0yz. Okay, so how do we decode this? Irrespective of the right hand side y, which is not known. So we are looking at what kind of solution will be possible. Let's try to find the rank of A. So to be rank of A, let's do two operations. We can have R1, we can interchange R1 and R2. 1, 2, 3, 0, 5, minus 1, 5, 1. R2 goes to R2 minus 2R1, which would give us 0, minus 4, minus 1, minus 1, 5, 1, 1, 2, and 3. And then we want 0 here. That gives me R3 goes to R3 plus R1, which is 0, 7, 4, 0, minus 4, minus 1, 1, 2, and 3. Right? And so we have R3 goes to R3 minus or plus R2 by 7. Not 7, 4, right? So that gives us 0, 0, and this will be surely non-zero. This is 0, this is non-zero, and so on. This is 1, 2, 3. So what we see is rank of A is equal to
2.
the last row is non-zero. So all three rows are non-zero.
It is 3.
It is 3. Okay, so now what can we talk about? What can we say about the rank of augmented matrix? Hmm? So rank of A is 3. Rank of augmented matrix will always be equal to 3. Right? And so in that case, the system will have solution. So out of this, which one should we go for? So do we want this? Will the solution be only if the right hand side matrix is something like x 0 0 or 0 y 0 or 0 y z? Okay, or it will be applicable to anything that goes into y, like y1, y2, y3. Yes.
So it's option C, sir, maybe.
It will be
Option 4, sir.
Option 3.
option 4 because there is no condition as such required on the right hand side because it is not getting affected because of what we have in A, the coefficients matrix. So given any y in any form, we will have solution of the system. Okay. Should I proceed?
Yes, sir.
So these were some examples of rank. Let's quickly define eigenvalues and eigenvectors so that we can build up on it tomorrow. Yes, so I'll talk about eigenvalues and eigenvectors. So if A is a square matrix of order n cross n defined over a field F, okay, then the scalar lambda will be called as the eigenvalue of A if there exists a vector, non-zero vector, okay, such that AV is equal to lambda into B. So this lambda is the eigenvalue of the matrix A and V is the corresponding eigenvector. Okay. So ideally what happens is this eigenvector when multiplied with A simply scales that vector and doesn't do any kind of additional operation. So if we happen to see this in terms of diagrammatic representation, so if this is my vector V, okay, then A into V, A applied on this vector will only scale the vector, could be in the upward direction, it might scale it up or scale it down depending on the value of lambda, and also positive or negative will accordingly change the direction accordingly. But the vector itself will not change, the vector will remain same, it will be only scaled, it will be only stretched by the factor of lambda. Okay, so can bring it down to AV minus lambda V equal to 0. So taking V common, we'll have A minus lambda I into V equal to 0, okay, which implies since the vector is not equal to 0, the determinant of A minus lambda I will be equal to 0. Okay, and this will generate a polynomial in lambda, and the polynomial will be called as characteristic polynomial. Of the matrix. So if we have a matrix like this 1 2 0 1, the determinant of A minus lambda I would produce a 2 cross an order 2 degree 2 polynomial, so which would be the determinant of 1 minus lambda 2 0 minus lambda, producing 1 minus 2 lambda plus lambda square. Okay, so that's the characteristic polynomial of A in this particular case. Okay, and it's very clear that the roots of this characteristic polynomial will be the eigenvalues. So in case of a matrix of order 3 cross 3, the determinant will be of order 3 cross 3 and will produce a cubical polynomial. Now we can obtain this polynomials, we can obtain this characteristic polynomials in a simpler way. That is, if we are dealing with a matrix of order 2 cross 2, then the characteristic polynomial would be given by lambda square minus the trace of the matrix plus the determinant of the matrix. And if you're dealing with 3 cross 3 matrix, then the easier way would be to calculate lambda cube minus sum of principal diagonals into lambda square plus sum of minors of diagonal elements into lambda minus the determinant of the matrix would give us the polynomial, the characteristic polynomial. Okay. So additionally, we have a theorem called as Cayley-Hamilton theorem. It states that the characteristic polynomial, every matrix will satisfy its own characteristic polynomial. So if the characteristic polynomial is some lambda cube minus something, we can replace lambda with A, the matrix A, and accordingly the equation will satisfy that particular polynomial. So what we saw in the previous case for the matrix, for this matrix which is 1 2 0 1, so for matrix A which was 1 2 0 1, the characteristic polynomial was lambda square minus 2 lambda plus 1 equal to 0. So by using Cayley-Hamilton theorem, we can say that a square minus 2a plus identity is equal to a null matrix, which becomes a very important statement because a lot of things can be deduced from this. Like we can find the inverse of the matrix, and we can also find some higher order expressions involving matrices by using this statement, because we know that this expression is equal to 0. Now, there are two important things that we can talk about. One is the algebraic multiplicity and the geometric multiplicity of eigenvalues. So AM and GM, algebraic multiplicity and geometric multiplicity. So in case if we have characteristic polynomial of a matrix that's denoted by a characteristic polynomial of in terms of lambda and is given by something like lambda minus 1, lambda minus 2 and lambda minus 1. So in such case, there are two eigenvalues. One is lambda equal to 1, the other one is lambda equal to 2. Okay, and the algebraic multiplicity for lambda equal to 1 would be 2, because that 1 is appearing 2 times. Okay, and the algebraic multiplicity for lambda equal to 2 would be 1, because that is appearing only once. So the number of times the eigenvalue is repeated, okay, is accordingly the algebraic multiplicity. If it is equal to 1, it's called a simple eigenvalue. Okay, otherwise, it's a eigenvalue with given multiplicity. Now, with every eigenvalue, there will be a corresponding eigenvector. Okay, so we can define the term, the geometric multiplicity based on that. So the number k of linearly independent eigenvectors associated with an eigenvalue of multiplicity, some multiplicity, will be accordingly termed as the geometric multiplicity of the vector. So the number of linearly independent vectors associated with the given eigenvalue. So sometimes, most of the times, the distinct eigenvalues will have only one associated eigenvector. But in case of non-simple eigenvalues, the number of eigenvectors can be more. Okay, so accordingly, the geometric multiplicity will be more than one in that case. But overall, in general, we have this relation that the geometric multiplicity is always lesser than or equal to algebraic multiplicity. Also, the geometric multiplicity is given by n minus the rank of A minus lambda I. So we can use this relations indirectly to calculate some intermediate values and so on, or to prove some statements. Let's quickly look at some properties of a matrix. So sum of all the eigenvalues. That's lambda 1 plus lambda 2 plus lambda 3. If we are dealing with a 3 cross 3 matrix, would be equal to so if I'm talking about a 3 cross 3 matrix, the sum will be equal to sum of the eigenvalues will be equal to
Trace of the
the
matrix.
trace of the matrix, and the product will be equal to the determinant.
Determinant.
Yes. Also, if one of the eigenvalue is 0,
Then determinant is equal to 0.
0, which means the matrix is
Singular
singular.
and non-invertible.
Yes. In case if we are dealing with a non-singular matrix, so if A is not equal to 0, and if lambda is eigenvalue of A, then we can say that lambda inverse is the eigenvalue of A inverse. Likewise, we can also in general case, lambda raised to n will be an eigenvalue of A raised to n. Okay, and we have already seen in case of orthogonal matrix or in case of unitary matrix, the eigenvalues are this. We know that the determinant is equal to plus or minus 1, which can be used to fetch out the eigenvalues. Okay, for nilpotent matrix, eigenvalues are
0.
0. If we are dealing with a triangular matrix, then the product of the diagonal elements. For idempotent matrix, it is 0 or 1. Okay, now additionally, eigenvalues of skew symmetric matrices. Okay, before that, if we are talking about a symmetric matrix, so eigenvalues of symmetric matrix are always real. And if we are dealing with skew symmetric matrices, the eigenvalues
0
will be
or
pure.
complex. Purely
Yes,
complex.
purely
Purely
complex.
imaginary.
Purely imaginary. Okay, and if we are dealing with an orthogonal matrix, the eigenvector corresponding to different eigenvalues are orthogonal to each other. So the dot product will be equal to 0. We'll just quickly talk about two more things and then we'll stop so that we can do a large number of problems tomorrow. So I'll talk about minimal polynomial.
The eigenvalues of Q Hermitian matrices will be complex always.
Will be complex.
Okay.
So minimal polynomial. So this is nothing but a monic polynomial with leading coefficient, which is monic polynomial is nothing but a polynomial with leading coefficient 1. So this will be a monic polynomial of lowest degree okay, such that which will satisfy the matrix. So let's say minimal polynomial is denoted by M, and so this minimal polynomial will be a polynomial of lowest degree which will satisfy the matrix. So M of A will be equal to 0. So since this is a polynomial of least degree, it will divide the characteristic polynomial. So M of lambda divides the characteristic polynomial of the matrix. Okay. So in case if we have a matrix like this 2 0 0 2. Okay. So here in this case, for this matrix, what will be the characteristic polynomial? It will be
2
lambda
minus
minus
2 minus lambda.
the whole square. So the minimal polynomial in this case has to be either lambda minus 2 or lambda minus 2 the whole square, either of this. Okay, so we can check whether this one, that is lambda minus 2, satisfies A or not. So if I check A minus 2i, okay, which is 2002 minus 2i, 2002, which is equal to 0. So since A satisfies this, accordingly the monic polynomial, the minimal polynomial will be lambda minus 2. Moreover, we can define an additional polynomial which is annihilating polynomial. Okay, so this is any other polynomial, let's say f of lambda, which is not equal to 0, and this polynomial satisfies the matrix. So any other polynomial apart from characteristic or monic polynomial, or in general any polynomial which satisfies the matrix will be called as annihilating polynomial. So what will be the relationship between minimal polynomial and annihilating polynomial? Will annihilating polynomial divide minimal polynomial?
The minimal polynomial will divide annihilating
Yes.
polynomial.
Minimal polynomial, which is the polynomial of lowest degree, which
Hmm.
satisfies A, will divide the annihilating polynomial.
Yes, sir.
Okay, so we've seen 3 polynomials and some properties of eigenvalues, eigenvectors, and we'll see examples based on this, how different problems can be asked on this properties and connecting everything that we have seen till now. Okay, so tomorrow we'll try to cover up a lot of problems, and then we'll see the applications of all these topics in some popular fields like AI, data science, and even statistical analysis. Okay, so we'll stop here for the day. Any questions till here?
Sir, can you explain annihilating?
Yeah. So this is any other polynomial.
With
Yes.
so with examples, you can.
Okay. So in case if there is a matrix of order maybe 3 or any other matrix, if it satisfies A cube equal to a square plus I. Okay. Then in such case, f of lambda equal to lambda cube minus lambda square minus 1 can be called as annihilating polynomial of A. So right now, see, A is not known and we have no information about its characteristic polynomial. We have no information about its minimal polynomial. But we can see that A satisfies this particular type of relation. Right? So this is the annihilating polynomial that we have extracted from this. Okay. Will A satisfy this relationship? A already satisfies this. Will A satisfy this also?
Yes, sir.
Yes.
Yes. So
Yes, sir.
can we have one more annihilating polynomial based on this? Let's say f1 of lambda, which will be lambda raised to 4 minus lambda cube minus lambda. So any non-zero polynomial which satisfies the matrix will be called as annihilating polynomial. Is that clear?
Yes, sir.
Yes.
Yes, sir.
Any other question?
If there are no more questions from the participant side, then we can wind up the session. Thank you very much, Mahesh sir, for yet another session of this. This was engaging. Thank you so much. I hope the participants have benefited from it. Again, we'll meet tomorrow for Mahesh sir's session, and the timings will be the same, 7 to 8. Thank you, participants. Thank you, everyone.
Thank you.
Thank you. Bye.